Hi guys, today we are talking about optimization in Unity, to be exact, mesh combining. We're going to look a bit deeper than the standard mantra, reducing draw calls is good. We'll break down the pros and cons of this approach and see how it fits in with the new tech in Unity 6. This video isn't about my assets, but about the technique itself. Okay, maybe a little bit about my assets. I will also be referencing the Unity documentation and official books throughout the video to make sure everything I'm telling you is backed by facts. But before we dive into mesh combining, let's define exactly what we're optimizing. If you already know the basics, feel free to use the timecodes to skip ahead. First, the mesh. By mesh, I mean the set of vertices and triangles that we send to the GPU. Next, the shader. This is a program running on the GPU that decides how to draw the mesh. Think of shaders like classes in C#. A shader defines a template, like numbers or textures, but it doesn't store the actual values itself. Then we have the material. A material is an instance of that shader with a specific value set. Following our C# analogy, if the shader is a class, the material is the object. A good example is a standard URP lead shader. You can create many materials from this one shader. They might look completely different, but the code running on the GPU is exactly the same. Now let's talk about the graphic object or just object. For the GPU, an object is always one mesh plus one material. You might see game objects in Unity with one mesh and multiple materials. If you look closer, that mesh actually has submeshes. They share vertex data but have separate index buffers. Basically, it's just a container. To the GPU, the information is still sent as separate one mesh plus one material pairs. Now that we know what and how to draw, let's understand the process itself and find the main cause of performance issues. For the GPU to work, the CPU must collect and send the data. This is called a draw call. The official Unity docs break this down into two steps. First, update the render state. The CPU prepares everything: shaders, textures, buffers. This is the most CPU-intensive step. Second, submit the draw call. The CPU simply tells the GPU what to draw. Let's turn off the Unity optimizations and look at the frame debugger. See this? Every time we draw a mesh, a draw call happens. If optimizations are on, Unity tries to be smart. Instead of sending data piece by piece, it sends it in one go to avoid changing render state constantly. If several objects share the same material, Unity sends them as a group. Let's enable static batching. See the difference? Objects with the same material are drawn in a favor calls. Unity combines them, but this process is automatic and we don't have any control over it. That is why the stats window shows batches, not raw draw calls. Batches are the actual commands groups that reach the GPU. Every time the CPU switches the current shader, a SetPass call occurs. This is the most expensive operation. Every time we draw a mesh with a new shader, the SetPass count goes up. You can see this number in the Unity stats window. To make this simple, let's use an analogy. The CPU is a manager and the GPU is an artist. Every time the manager says draw a cube, that's a draw call. Giving 10 separate commands for 10 cubes take a long time. To speed up, the manager can say draw 10 red cubes right now. This is a batching and it's much faster. But when the artist needs to change paints, that is a SetPass call. They have to wash the brush, open a new tube and mix the paint. That takes the most time of all. Now finally, let's move on the mesh combining and how it solves this problem. As we find out, it's much easier for the GPU to handle one drawing command with a large set of data than many commands with the small bits of data. Technically, it is faster to draw one complex mesh with 50,000 indices in a single command than to process hundreds of commands for small meshes with 100 indices each, even if the total number of indices is exactly the same. Performance is often limited by the number of commands. Each little piece demands attention from the CPU. On mobile devices, this resource runs out very quickly. This is where mesh combining helps us. It is a simple but very effective technique. We just merge meshes that share the same material into one single large mesh. Once combined, we don't need to do any extra calculations. The data is pre-packed and ready for the GPU to process instantly. Let's combine the meshes in the scene using one of my tools and check the frame debugger. See that? Just one draw call. To summarize, mesh combining allows us to have more objects in the frame by reducing the number of draw calls. Sometimes we can go even further and perform a two-step optimization. Before combining meshes, we can combine the materials first. Here is a simple example. We have two objects using different materials. Drawing them takes two draw calls. We cannot combine them directly. However, they use the exact same shader and settings, only textures are different. So here is the solution. First, we merge two textures into one big image. This process is called texture atlasing. Next, we create a single material using this atlas. Then, we adjust the UV coordinates of the meshes. This tells each object to use its specific part for the texture atlas. Now that they share one material, we can finally combine the meshes into a single object and render it in just one draw call. Now let's move on the downsides. Unfortunately, they do exist. But before we discuss them, I need to make a very important point. If you open the Unity documentation or read the optimization ebooks, the very first chapter is always called profiling. This is not a coincidence. Before optimizing anything, you must identify exactly where your bottlenecks are. The second rule you will read is always test on your target device. Data from a high-end PC is often useless if you are building a mobile game. I will add a third rule. Always understand what you are doing and why. Please remember, mesh combining is not a silver bullet, it's just a tool. And like any tool, if used incorrectly, it can actually make your performance worse. Let's get specific. The first issue relates to Frustum Culling. This technology is on by default in Unity. The idea is simple. If an object is completely outside the camera's view, we don't draw it. But there is a catch. If even a teeny part of the object enters the camera view, Unity renders the whole thing. Look at this. Only a small corner is visible, but the vertex count spiked immediately. You can see where I'm going with this. By combining small objects, we create one massive mesh. The GPU has to process the entire mesh, even if we only see a small edge of it. That is why you need to be smart about how you group your objects. Usually, Frustum Culling is invisible to us, but I wrote a script to visualize exactly how it works. The solution I use in my tools is a cell-based combining. We simply divide the scene into a grid and only combine objects inside these cells. This isn't a perfect fix, but modern GPUs can easily handle a few extra thousand triangles. However, the number of draw calls is usually much more critical. Therefore, it is important to choose the right cell size to find a balance between draw calls and the triangle count. Now, here is important nuance we talked about earlier. If we combine the entire scene into one object right now, we get a very few draw calls and huge FPS on the PC. Even inside the build, my powerful computer runs it perfectly. Does this mean we found the optimal solution? Absolutely not. Remember, always test on your target device. Right now, the whole scene is just one object. No matter where you look, the GPU renders the entire world. My PC can easily handle 100,000 extra triangles, but the low-end mobile devices will struggle. Optimization books suggest testing on both your minimum and maximum spec devices. Optimization, just like a programming in general, is always about finding the right balance. Memory usage is the only downside that is truly hard to mitigate. Let's picture a scene with 100 identical barrels. How does Unity store this? It keeps the mesh data in memory once. The 100 barrels act as instances that just refer to that data. So, if a barrel has 1000 vertices, the RAM holds just 1000 vertices plus 100 references. But if we combine them into one object, we create a single massive unique mesh. This new mesh physically stores the data for all the barrels. That means 100,000 vertices taking up space in your RAM. So here is the rule. Combining identical meshes multiples memory usage. Combining unique meshes has a much smaller impact. This is why profiling is essential. You need to ask yourself, can I trade some RAM for better FPS? It's usually a trade-off we have to accept. However, my tools offer a partial solution called lightweight buffers. This approach doesn't reduce the number of vertices, but it significantly reduces the size of the data they take up. For example, in Unity, a normal vector usually takes 12 bytes. With lightweight buffers, we compress it down to just 4 bytes. Now let's look at Unity built-in solutions. What are the pros and cons, and is manual mesh combining still relevant? Let's start with static batching. It's simple, enable it in the settings, mark your objects as static, and you are done. Let's check the frame debugger. Confirm the objects are combined. The benefits are similar to manual combining, but with one major advantage. Unity still handles Frustum Culling effectively for these batched objects. The main downside, it's a black box. It's hard to predict how it will behave, and we have zero control over the process. Plus, it still performs calculations at runtime, adding CPU overhead we want to avoid. I checked the Unity documentation and found these key limitations. Objects must be static and share the same material. Skinned meshes are not supported. Batching for transparent objects is often limited. Objects with negative scale usually won't batch. There is a limit of 64,000 vertices per batch. This is fine for mobile, but modern PCs and consoles can handle much larger meshes. And the tricky one, vertex attribute layout. The meshes must use the same data structure. If mesh A has normals and mesh B does not, Unity will not combine them even if they share the exact same material. Next up, GPU instancing. This is supported by default on most modern GPUs. The concept is simple. Say we need to draw 100 trees. Instead of sending 100 separate commands, we send just one. Draw this specific geometry using this material at these 100 locations. This packs many objects into a single draw call without eating up RAM. Because we store the vertex and index data only once, we just send the geometry and an array of positions to the GPU. The critical downside, objects must share the exact same mesh and material. This makes GPU instancing useless for unique objects, but extremely powerful for repetitive ones. There are other limitations to keep in mind. Skinned mesh renderers are not supported. Shaders must support instancing. Most built-in shaders do, but if you write custom ones, you need to add support manually. And the third point is CPU overhead. If we use standard automatic instancing by checking the box in the material, Unity still calculates Frustum Culling of the CPU for every single object. Of course, you can go to the hardcore way and use graphics draw mesh instances. In this case, Unity does not waste CPU time on culling. It stops doing culling altogether, unless you write your own culling logic, for example using compute shaders. Now let's move on to the latest Unity systems designed to eliminate lag. Meet the GPU resident drawer. This is not just another optimization tool, it's a complete new approach to rendering. It serves the foundation that enables other features like the GPU occlusion culling. Let's analyze it step by step. First, let's look at the GPU resident drawer separately from the SRP Batcher. According to the Unity documentation, it automatically uses the batch render group IP to draw game objects using GPU instancing. This reduces draw calls and frees up CPU time. So, to put it simple, in isolation, the GPU resident drawer is basically GPU instancing with all its pros and cons. Now let's talk about the SRP Batcher. This is truly an impressive piece of tech in Unity. But there is a huge misconception here. It's critical to understand. The SRP Batcher does not reduce the number of draw calls. Its goal is to make these calls cheaper. Instead of reapplying data from CPU to GPU every frame, it keeps the data persistent on the video card. Let's fire up the frame debugger. At first glance, we see a very small number of SRP batches. Looks great, right? But look closer. Inside you will see a whole list of individual draw calls happening. Yes, each call is now cheaper for the CPU, but remember, cheap does not mean free. The calculations are still happening and the workload is still there. Overall, the GPU Resident Drawer and SRP Batcher are truly sophisticated systems. They try to automate optimization and take the load off our shoulders. However, their main downsides comes from their biggest strength. They are effectively black boxes. Once enabled, we have almost no control over what they do. The system makes decisions for us, and crucially, those decisions consume CPU time every single frame. In contrast, manual mesh combining is like a rock. It's simple, solid, and effective. It doesn't rely on complex logic to work. You combine the objects once and you are done. It's bake it and forget it solution. No extra calculations, no runtime overhead. Let's look at a comparison. I will use this massive city scene. I will leave a link to the asset in the description. The goal of any tool is to render more objects with less lag. So, for this stress test, I will move the camera up to see the whole city at once. First, let's turn off all built-in optimizations. Here is our baseline FPS. Now let's enable the GPU Resident Drawer and SRP Batcher. I will also test with and without GPU culling. Result, the FPS has improved significantly. Now let's apply manual mesh combining and texture atlasing. Look at the result. As you can see, the FPS is even higher. So, what's the main takeaway from this comparison? The built-in solutions, especially the new features in Unity 6, are really good. They work perfectly if you just want to throw objects into the scene and save time. They will boost your performance. However, they do not provide the absolute best result you could achieve. If we want to go a bit further and be a bit more professional, we need to do more than just click a checkbox. By analyzing the scene and applying proven manual techniques exactly where they fit best, we can unlock performance levels that are simply unreachable by automation alone.